Okay, so today we're going to talk about what are called repeated measures designs, which are really pretty simple to understand as far as, I don't necessarily mean about the mechanics of them, but the idea of how the designs work is pretty straightforward. Let's say you're interested in learning and forgetting, right? Independent groups won't really do, because learning is change over time. Forgetting is change over time, and it's within the same subject, right? So you can't really use independent groups. You can't use two separate sets of people. You can't look at the group that's had one trial, the group that's had two trials, and the group that's had three trials. You wouldn't do that. That would be, it's counterintuitive. It doesn't make any sense. You can kind of do that, but it's not going to tell you as much as, like, learning is about change over time within the same thing. So we can't use independent groups. So what you're going to have to do is test the same people over and over again. Okay? There's really no other way to do this. So any kind of change over time. And we see that with a lot of other things we look at. You can look at fatigue. You can look at changing things like reaction time with different drug dosages. It's a pretty common thing, actually, in neuropharmacology. So whenever you're looking at change over time, you're going to have to test the same subjects, people, rats, whatever, over and over again. So you're going to get something like this, which is just, let's say you've got a 5-minute retention interval, a 1-hour retention interval, and a 24-hour retention interval. This is actually pretty common in sort of memory research. You have to just have people give them a list of words, give them a 5-minute retention, give them a distractor, a 5-minute retention interval of some sort, the distractor, then you can test them. Then you can give them a 1 hour. 1 hour later you can test them, then you can test them a day later. It's not uncommon. So what you're going to get is a forgetting curve, right? Discovered by Ebbinghaus. So we used to always have group 1, group 2, group 3. Now we've got group 1, group 1, group 1. It's the same group being tested over and over again, right? They're not tested just one time, they're tested 3 times. Okay. So do you understand the design? I think it's pretty straightforward. All we've done is, instead of doing a design where we have different subjects in different groups, or within different levels of the independent variable, we have the same subjects within each level of those variables. Okay? All right. Questions so far? Yeah, that's pretty straightforward, right? Okay, now there is a potential problem here, and that's that observations are no longer independent. You know how much I'm harping on, and you cannot be able to guess this score by knowing this score. Well, if I'm testing Wendy 4 times, I think by the time I get to the 4th one, I've got a pretty good idea what the 3rd, 2nd, and 1st one are, because it is all Wendy, right? So let's say it's about memory. Everybody's memory is a little bit different in this room. Right? So if we were doing a memory test, and let's say Wendy has some sort of super memory, and her decay function isn't hardly decays at all. Okay? Let's say Kelsey's is not as good, so it's more like normal people, so it just decays some, whereas she's got super memory. So, and then we look at we got Ashley's scores, and then again look like normal, going down, whatever. Point is, I can make a pretty good guess by looking at the first couple of scores if I know it's within Ashley or within Kelsey or within Wendy. And I keep saying, you can't have that. You can't have that. Independent observations. That's right. The observations are not independent. In fact, they're completely dependent. They're within the same person. So what we do is we actually just put it in the model. The reason we couldn't have it before is because there was nothing in the model that said, about dependent events. Well, we're going to just put that in the model. That's all we're going to do. Just going to throw that in. Okay? So the model's going to look like this. It's going to be x equals mu plus tau, that's our treatment, plus pi, that's for people, plus epsilon. That's error. So now we just have an effect of people. We have a variable called subjects, we'll call them, and they have different levels. And one level is Wendy, and one level is Ashley, and one level is Kelsey. Huh. Wow, that's kind of cool. X equals mu plus tau plus pi plus epsilon. So any score equals the grand mean plus the treatment effect plus the error. And of course, here's the new part, effective subjects. This, if we took that out, the pi, right? If we take that out, it's back to the same vanilla one-way analysis of variance I talked to you about 2.5 weeks ago, 3 weeks ago, right? It's right back to the same thing. But what we've done here is we're at the same subject, so we're just going to take that into account by putting this term in the model. Okay. Questions about this? Okay, that's good. So like I said, I think conceptually it's a pretty straightforward idea, especially ever since going back from the other kind of ANOVA that we were dealing with before. All right. So now the design looks like this. I'm just putting in a new variable called subjects. Subject 1, subject 2, subject 3, subject 4. I'm going to say we test 4 people. And at 5 minutes, 1 hour, and 24 hours. So we've actually decreased epsilon.
Is that a good thing? That's a good thing.
Well, sure, because that's error. We want error terms to be small. Because think about this. The old version, doing this, the standard sort of one-way analysis of variance would look like this. X equals mu plus tau plus epsilon. Well, the new model has x equals mu plus tau plus epsilon plus pi. There's only one place pi can come from. The oven. It can only come. This is here. It can't come from there. It's the only place it can come from is here. So what we've done is we've split error up and made it smaller. We don't want error. Right? Error, well, it's not bad or anything. In fact, like I always said, variance is our friend. But the problem is we are always dividing by this, aren't we? We're always dividing by something with epsilon in it, the bottom. Right? It's always in the numerator, denominator. The bottom of the fraction. So we're dividing by. When you divide by a small number, you get a big number. Big number's good. Big F. Happy, happy, joy, joy. Did anybody get my Ren and Stimpy reference there? Probably not. Probably before you were born. Certainly before you were born. You ever seen Ren and Stimpy though? You should. It's funny. Oh, sir. I don't like it. That's a horse that shows up and just says that now and then. On Ren and Stimpy. You idiot! It's a great cartoon. Okay. So we've split this off. We've made this smaller. That's good. Problem is, we're paying for it. There is no free lunch. There is no free variance. There's no free pie. You must pay for your variance reduction in degrees of freedom. So what you've done here, you'll probably make your F bigger in the end, which is a good thing. But that also means, because the degrees of freedom for this go down, because we split this apart for error go down, our critical value of F is going to get bigger as well. So while we get a bigger obtained F when we calculate it, we also have to exceed a bigger F, because we've paid for it by decreasing the degrees of freedom for error. And I'll show you this in a second, this in a more concrete way, in just a moment. So we have to pay for it. We can't decrease error without paying for it. So if we did this experiment, and on the left here we have the standard one-way analysis of variance. We actually could analyze it this way. We would be violating the independence assumption, but we still could analyze it this way. The numbers don't know that. Retention interval has 2 degrees of freedom. Error has 9 degrees of freedom. We're going to take this mean squared for retention interval. We're going to divide by mean squared error. Right? So we're going to find I don't know what the critical value is for F at 2 and 9 degrees of freedom. I don't care, but I know it's a smaller number than the F at 2 and 6 degrees of freedom that we have over here on the right, which is the way we do it with the repeated measures design. We now have another variable here called subjects. We have 4 subjects. Remember the design I made up had 4 subjects. So we're going to have little n minus 1, 3 degrees of freedom for that. Retention interval is going to have 2. Remember, the tau stays the same. Error has been split off. Look, 9 degrees of freedom, 3 and 6 is 9. Hey, I told you where it came from. Okay. You got a question, Wayne? You good?
No, she had a question.
Jay, you have a question.
I got it answered.
You got it good? Okay, so that's good. Remember this microphone, it'll be all over YouTube. You'll hear it. Yeah. You're famous. You're all very famous. Tens of people have watched these videos. The audio's literally thousands of people, but the videos are only tens so far. Okay. Questions about this? Do you see what happened here? Right? We split off error into people and error, and that's what we get here. Look, we split the degrees of freedom off too. Yeah, guys.
Why is the total the same number, just like for that example?
For any example, because any design has a finite number of degrees of freedom and a finite amount of variance, and we're just splitting it in a different way.
Did you just get 2 randomly for the retention number? Did you just throw that in?
Oh yeah. I mean, because I use 3.
Okay.
I use 3 levels, right? 5 in 1 hour, 24 hours. So 3 minus 1 is 2.
Okay.
Yeah. So we have, remember, we have 4 people tested 3 times. That's 12 observations. We have 11 degrees of freedom. Okay. Any design has a finite amount of variance and a finite amount of number of degrees of freedom. And that doesn't change. I mean, within any design, within any set of data, there's variance. It's how you split it up and then how you analyze it, which is why we call it analysis of variance. Okay. It says that right there. And a finite number of degrees of freedom. We have a partition of degrees of freedom and the variation of the variance just a little bit further. That's all we've done with this kind of design. We just partitioned it a little further. And you can't always do this. You can always do this in this case because we have repeated measures. We have the same people. We have another variable we can throw in the model, which is people. Pi for people. Pi for the people is what I say. Mean squared for retention interval will actually be the same for both of those analyses I had there. I didn't give you numbers, but if you made up some numbers, they would be exactly the same. Those numbers would be the same. Have the same number of degrees of freedom, variance is going to be the same, you're going to get the same mean squared. The question you're going to ask is the reduction in mean squared error worth the loss of degrees of freedom for error? Because again, the smaller number of degrees of freedom you have, the bigger the critical value you have to exceed, right? So it makes it a little harder to exceed it than if it's bigger, but you've also made the number you calculate bigger. You've also made the number you calculate bigger. And it's almost always the case that yes, it is. Does anybody have their book on it? We can look it up. So, let's see. It's all beautifully tabbed. It's nice. Let's see. Is it the F table there? And that's T. Where's F? Square T. Boxing T, blah, 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 blah. I'm throwing multiple comparisons.
Maybe it was before G.
Maybe it was.
Oh,
Oh, the F is right on the very back? No. That's. Looking for the F.
check the next page. I think I sticky noted it.
Oh, it's this one here? Oh, yeah, F. Yeah, here it is. Okay. So, let's see. So we're looking at, what, 2 and 6 degrees of freedom versus 2 and 9. So 2, 1, 2, and we get 8 here. That's fine. It's round. What am I doing? I'm not reading this wrong. Oh, no, I see. Oh, that's the non-central F. There we go. There's the F. Okay. And that's a pi squared. Oh, here's the F. Okay. 2 and 9, finally. So for the one-way analysis of variance, it would be 426. It's 426. Okay? Now, we have to exceed. For the repeated measures, which was 2 and 6, it's 5.14. So you see, we have to exceed a bigger number now. Thanks, Ron. So that's going to be a little bit harder to do. But we've made the bottom of the fraction, I think that's the denominator. We've made that smaller, that's going to make our obtained f bigger. So it's probably worth doing. In fact, it's almost always worth it. But you can't do it, it's not like there's no price. Okay. So think about this a bit. Okay, so now that I've introduced the idea, is it actually reasonable to think that this is true? X equals mu plus tau plus pi plus epsilon. In other words, shouldn't there be an interaction? In fact, when I told you guys about the idea of the different subjects and different group, same subjects in getting tested over and over, I said, in fact, that Wendy had super memory, right? But you guys didn't have super memory. You had normal memory like me. That means there's an interaction between level of person. When I say level, I don't mean that she's better than you or worse. I refuse to make judgments. You're all special snowflakes. But, in fact, what I described was exactly an interaction of people and treatment, wasn't it? It's exactly what I described. Right? So, because I'm saying that different people, different subjects, different levels of subject, have different decay functions. That's a two-way interaction. That's exactly what that is. And there's nothing in here about tau by pi. We should have, it's much more reasonable to assume that we have interactions that way. There probably are situations where this is true, but it's more likely to assume that, in fact, our model changes. It's much more simple to say x equals mu plus tau plus pi. Tau pi is delicious. I'll stop making pi jokes eventually. By eventually, I mean 2017. Well, 2016, yes, because I'm not teaching this next year, because I'll be on sabbatical. Screw you, Dupuy, you get to make the pi jokes. And that's partly that, and that's also partly because Paul eats a lot. He's a little. Gotta have fun with it. He makes blind jokes all the time about me, which is fine. I'm cool with that. Tom.
Should epsilon be in that model?
Aha! No epsilon? Yep, no epsilon. It's an excellent question, and I guessed it. X equals mu plus tau plus. But this sort of looks, by the way, like the back of a Russian hockey sweater somehow, doesn't it? We've exhausted the degrees of freedom. They're gone. There's a finite amount of degrees of freedom in the model, and we don't have any left over for epsilon. We've basically treated subjects just as another variable. And what happens is, retention interval 2, subjects 3, retention interval by subject 6. Oh, that adds up to 11. We have nothing left. We don't have anything left for error. Note, by the way, that this has 6 degrees of freedom, and it's actually calculated exactly the same as you would if you had a mean squared error. So it actually is the same thing. But it really is an interaction between subjects and retention interval, in this case. But yeah, we actually don't have an error. There is an error term here. It's right here. Retention interval by subjects. We're going to divide the mean squared for retention interval by mean squared for retention interval by subjects. That's what we're going to actually do. But it's the case that it's no longer something we just call mean squared error. We calculate it by calculating an interaction between subjects and the treatment. In this case, subjects and retention interval. Yeah, I know it looks weird to not have epsilon in the end. But we don't have anything left we haven't explained. We've now explained all the variance. Epsilon is unexplained variance. We don't have any of that. Explained everything. So how does this work? I mean, it's different, right? So our error term is actually a treatment by subject interaction. Subjects are a random factor. They're a hell of a lot more like a random factor, at least, than retention interval. We can treat them as a random factor. So the expected values of the mean squares work out such that we divide retention interval, because of the expected values, by subjects by retention interval. In fact, if I worked out the expected values, or I showed you the expected values, the expected value of mean square treatment is going to be this. No, sorry. Tau plus variance due to tau, due to treatment, plus variance due to treatment by pi interaction, and the expected value of the mean squared for the treatment by subjects interaction actually just equals the interaction. We divide this by this. Remember the other day I told you all this stuff about expected values of mean squares with mixed effects models? And you wondered why I told you? That's why. Besides the fact that it's something you should know, it actually is useful to know that because it shows you why we can use this as an error term. We're going to divide mean squared treatment by mean squared for treatment by subjects. Okay? Questions? Ashley?
I was trying to write down what you said, but I think I missed the bottom part. It was divide retention interval by subjects by...
Retention.
Oh,
By
okay,
mean
so-
squared for retention interval. By mean squared for subjects by retention interval in this case.
Okay, thank you.
Yep. Okay. We don't test the subject factor. There's a mean square for subjects. It gets calculated. It's variance we've removed, but we don't test it. We don't test it. So you just leave it there on its own with the subject's mean square going, "Don't leave me hanging, bro." Anybody who says that, they're not your friend. You should go away. Get away from them. They're not people you want to talk to. They're from a 90s movie. See, we can't test mean squared subjects. The expected value, by the way, for mean squared subjects is pi. So let's put that in here, by the way. So expected value mean squared for subjects is. You see anything to divide by? No, there isn't one. There's nothing to divide. There's no error term. So first of all, we can't do it because there's no error term. There's no correct error term. So we have nothing we can divide by that would make any mathematical sense. Secondly, who the hell cares? What would be your magical discovery? People are different from each other. Ooh, call the Nobel people. Yeah, subjects are different. That's why we're taking out their variance. If subjects weren't different, we just test one person in every experiment we do and go, well, people are just like that. Right? The plural of anecdote would be data in that case. We don't just test one individual, we test many individuals. Right? So who really cares? This would not be an interesting discovery even if you could discover it. Oh boy, people are different. Yeah. Ooh. Call science and nature. Don't worry about it. So not only is it impossible mathematically to do, it's also uninteresting. So it's not even a problem that way, just simply uninteresting. We can say how much variance we've explained due to people, but we can't say if it's a significant effect or not, and we don't care. It will be a large chunk usually, right? Because we've taken out the fact that Wendy has super memory, and we've taken out the fact these two are just, normal. Mundanes, as they would say on Babylon 5. Whereas the Psycops the Psychor will be coming to take Wendy away to grow up with the Psychor. None of you watched Babylon 5, did you?
No.
No, I don't care. It's the greatest science fiction show ever made. You just got to get past season 1, which is really, really rough. Season 3, 4. There are parts I can make my wife cry by mentioning one episode to her. I'm not even going to say it now because one of you might do that, and that would be me. But it was so moving that I can say, remember the time that? She goes, don't! You make me cry. And there's a couple that make me cry.
It's like the episode where Rose goes away from the calendar.
It's better than anything you're talking about. Okay, so this design is a pretty commonly used one. There's a couple people in the honors thesis that are using repeated measures type designs. They're a real nightmare to analyze with our software because we don't have good version of SDS we have doesn't deal with repeated measures very well. It can, but it doesn't do it well. Okay? So that just weird.
You mean like it makes errors?
What's going on? Everything okay? All right. You got a stock tip or something, Tom?
I think so, yeah. I don't know what one is up.
Oh well.
Yeah.
If it happens like 8 more times, I'm gonna break your phone.
I did.
I can call it. That's okay.
That's
I'm not that concerned. So randomized block design the repeated measures experiment is a special case, in fact, of what's called a randomized block design. So remember the matched pairs or correlated t-test? We've talked about that. That's where you match subjects up and you treat them basically as the same subject because you match them on some variable. Okay? So maybe if you've got animals, it'd be like litter mates, or it could be something like that we find that, we're doing, I think the example I used was like blood pressure, right? So we measure everybody's blood pressure and we find out people have the exactly same blood pressure and we treat them as the same person. This is what we're talking about. So subjects are usually matched on the dependent variable. So we can do the same thing like can we do with analysis of variance? It's the same idea. And we're basically just treating each, instead of matching up pairs of subjects, we're going to match up blocks of subjects. And we're going to have maybe 3 or 5 subjects that are the same. What we need here is what's called homogeneity of experimental units, which just means that, that's an assumption, it just means that, so if you 3 guys are a block, it just means that your scores are the same on the dependent variable. And now I'm going to give Jay one level of a treatment, I'm going to give Wendy another level of a treatment, and I'm going to give Tom a different level of a treatment. But if you weren't being treated at all, or you're all being treated the same, you would have exactly the same scores. That's what that says. And we do that by matching, like we set it up that way. So I can't just pick 3 random people and say you're in a block. What we tend to do is take 3 people and match them on something. Okay? And it usually is the score on the dependent variable. Let's say it was blood pressure, and we're going to give Jay a placebo. We're going to give Wendy her super memory, but that's very tough on her blood pressure. So we're going to give her some dose, and Tom's too calm, so we're going to give him something that just ups his blood pressure. I don't know.
Cocaine.
Yeah, we give him a lot of cocaine. That's right. That's right. We give Tom a lot of cocaine. There's no way Insert's giving me any money for this. It's not going to happen. So we can do it with like litter mates, matched pairs, twins, triplets, whatever. But typically we just match on the dependent variable.
What's litter means?
Oh, litter's like a litter of animals.
Oh, okay.
Yeah. So blocking. So we call this variable the one we block on. It's usually a nuisance variable. We block on nuisance variables. And I'll give you an example in a second, and you'll see why we call it a nuisance variable. It's a nuisance variable because it's something that gets in the way. It's a freaking nuisance, man. It's exactly what it is. It's something that gets in the way. It's going to add variance. It's variance we can explain and remove. Because if we can explain variance, we can take it out. So this again reduces the same sort of logic. This is going to reduce epsilon, reduce error. So that's going to give us greater power. Structural model is actually pretty much the same as the first one I showed you. It's funny because the repeated measures is the special case of the randomized block. So a structural model looks like this. Oh, yeah, it's exactly the same as the one we started out with. It's any score equals the grand mean plus the treatment effect plus the block that you're in, the blocking variable, plus the residual. So this time we have a block. We have blocks. We don't have block by treatment interactions. My knee hurts. Jesus. I'm getting old and my knees hurt. I actually gotta pop sometimes on movement. It's great. I don't feel any different than I did when I was 12, except for things like that. So, we got some assumptions. This is exactly as it always is. The sum of the treatment effects equals 0. That's just the thing. It's always going to be the way. They always sum to 0. The block, the variance to the blocks, or the effects of blocks, are normal and independent with a mean of 0 and a variance of, well, we've got to give it a name, sigma squared sub pi. We could have called it Kevin. We would call it sigma squared sub pi. And error is normally distributed independent with a mean of 0 and a standard deviation of sigma squared sub epsilon. So the only new assumption here is this guy here. It's just that the blocks are normally, the variance, like the blocks are normally distributed, the effective blocks. So those are random factors. This is a fixed factor. Errors are independent of blocks. So the differences, and they aren't really, I guess their individual differences are independent of what block you're in. You can't predict the individual differences based on someone's block. Okay? And again, so these guys are blocked because we blocked up their blood pressure the same. We block you guys up. And this way because we're going to have you included. Okay? We're not going to exclude actions. I'm trying to be inclusive. I'm nothing if not awesome. So there are also no interactions, and there are no tau by pi interactions. That model had none of that in there. So there's nothing about like different blocks are affected by treatments differently. Because we can't actually measure that. Because we have different subjects in each group, even though they're blocked on something, we actually can't measure this tau by pi interaction. So what if there are interactions? Well, then first of all, they're better than there shouldn't be. But if there are, there's only one place that can go, and that's into that error term. And we don't want it there, because that's going to make the error term bigger, and that makes it harder for us to find significant effects. And that's what we want to do. We want to find significant effects and publish our results and get a good postdoc, and then, after a while, get a few more publications, teach a couple classes, and then get a job. And keep publishing things, and then eventually you get tenure and promotion. I'm sort of describing my life here. You have kids, it's pretty successful, it's all good. Oh, you've met a wonderful woman, it's all great. Then it's all because you've decreased error. It's all because you've decreased error. Or guy, it depends, whatever you're into. I'm inclusive. You will lose power if epsilon goes down. If it goes up. Because it makes the fraction smaller. It makes the f value smaller. Or bigger. So, no, it makes it smaller. So don't have interactions in your data. That's going to be way easier said than done, because we can't measure if we have significant interactions, but I'm just telling you not to have them. So how practical is that? Well, not very. Let me give you an example. Okay? This is how you would deal with this. So let's say we have, and I've just made something up here, where we've got 3 different teaching methods. Okay, 3 different teaching methods. This will be the standard teaching method, the lecture. Okay? This is going to be the so-called flipped classroom. You know what the flipped classroom approach? You know this? Where you actually do all the reading and everything in advance and listen to a lecture in advance, and then you come to class and you work on stuff in class with the help of the professor. It's just a different approach. People do that a lot. It's a new thing. And we'll say this one here would be, what's the third thing we could do? Like online learning. Totally like online. Okay, I'm just making it up. I don't know. I don't think it would be the best. I don't think any of them probably did for that much, to be honest with you. I think it depends more on who's teaching you. So those are our three methods. Now let's say we're doing something with a language, and I think previous experience with a language clearly has an effect, right? Because, and I know my wife teaches French, and she says that sometimes there are people that have, like, she teaches like the intro level French sometimes, and the thing about that is that if you actually are a francophone, I don't know how you could take that class, because it'd be, you walk by the classroom and she's teaching people how to count and colors and things like that. And it's like, oh my God, how do you deal with that? So that's easy. Pretty easy, right? On the other hand, if you've really not taken a whole lot of French before, it's going to be hard because you're learning a new language. And some people maybe did French immersion for a while, so they have medium experience, right? So the low experience, we'd call that a block. That is a nuisance variable, isn't it? And we can actually say, how many years of education in French do you have? And if it's like, I don't know, what's the minimum? I think French is grade 10, is that right?
Just grade 9, I think.
Yeah.
Grade 9?
Yeah.
Okay. So you would have 9 years,
Oh, yeah.
perhaps, depending on where you go to school. Right, because in elementary school, you don't learn French from kindergarten everywhere. Depends where you live, right? So let's just say 9 years, and then you've got 5 years, and then you got like 1 year. Right? That's clearly going to have an effect, right? So we can, and we know there's going to be variance there. Why don't we explain it? Put them in blocks. And I said there can be no block by. There's an interaction there, isn't it? Right? Because the effect of a method changes depending upon the different experience the block people. You know, you worry if you don't. Right here, I would say, I think we should find a significant effect of method. It looks like generally the best one is method 3. If we don't find this, that's when I go, it's probably because error is too big because there's an interaction. If you do find something, you just don't worry too much about it. The worst thing to happen, though, so you'd probably be okay here. If you've got a disordinal interaction, lines are crossing, that's a problem. That's going to be a real problem. Because that means the interaction term is going to be big, that's all. And it's got nowhere to go but into the error term. All right? Okay. Questions? So this is like randomized blocks are special cases. Oh, sorry, repeated measure special cases, randomized blocks. Thanks.
I wanted to ask this, but a couple of slides back for the assumptions, I didn't catch what you said. The pi NID.
Oh, that means that the effect of blocks, right? The block effects are normal and independent, with a mean of 0 and a variance of sigma squared sub pi. We just gave it a name. I said we're going to call it Kevin.
Pi in that case, would that be 3.14? Or
No. No, it's this pi. No, it's not that. Yeah, pi for people. Pi for all of the people. I did it again. These horrible pi jokes. I do it every year and I hate myself for it. I feel like I've eaten a whole pizza or something. It's like self-loathing after I make these pi jokes. I'm serious. It's like I try to say things that are vaguely funny. I kind of pride myself on that. And then you say something like, pie, you don't like pie? It's kind of lame. You could use more than one repeated variable. Hey, this should look to people in the lab class vaguely familiar, except we only had 2 retention intervals, not 3, but we had an implicit task and an explicit task, and we had 5 minute, and we had 5 minute and a 5-day retention interval in that case. So an implicit task, an explicit task, a 5-minute retention interval, a 1-hour retention interval, 24 hours, and everybody gets every level of everything. Everybody gets both kinds of memory tests. Everybody gets both or all three rather retention intervals. That's not a complicated. That's a very common kind of design. It's a very common design, right? And like I said, you guys in the lab class, that's almost what we did, except we had 2 levels of retention interval. So what's the model here? X equals nu plus alpha plus beta plus alpha beta. Oh, that looks familiar, right? But now we throw in the effect of people. Plus pi plus alpha pi plus beta pi plus alpha beta pi. And again, the error's been exhausted. So the degrees of freedom are exhausted. We have no way to have an error term. An epsilon term. We have error terms. That's an error term, that's an error term, and that's an error term.
Why aren't they interactions?
They are interactions, but those interactions are error terms. We're going to divide by those mean squares. We're going to divide mean square A, for example, so retention interval, in this case, I guess, by the mean squared for retention interval A by subjects. There's a lot of terms here, many of them potential error terms. Those are the subject factor in them are potential error terms. So what do we test with what? Like, what do we divide by what? Well, you could, you certainly could work out all the expected values of the mean squares every time you do a design. Well, you could. You don't have to, but you could. Why would you do that? Well, you know, because you don't know any better. It would look like this. I'm assuming we have 10 people in that experiment that I had up there. Okay. We got. I'm listing this in a specific order. You list the subjects first, and then you list any repeated factors next. And then, so I get subjects first, done. No, I said assume there's 10 people in our experiment. 10 people. So we got 9 degrees of freedom. Retention interval, we had 3 levels, so now we have 2 degrees of freedom. Oh, look, subjects by retention interval. Stop. That's 18, obviously. Now, another variable, memory. That's the memory test type in this case, right? Implicit or explicit, so 1 degree of freedom. Memory times subject. Memory times retention interval. Memory times subject by retention interval. Memory times memory? We can't do that. Done. 9 and 2, right? 1, 9, 2, 18. 9, 10, 11, 29, 30, 49, 50, 51, sorry, 40, 51, 59. And there's 60 degrees of freedom in the whole, 60 observations, 59 degrees of freedom. We test, what this is telling us is we test retention interval. How do you figure out what you test with what? When you do what I just said, you list subjects first, then any within subjects factors next, you make the interaction, and then you keep doing the same thing until you're done. Right? So you go subjects, retention interval, subjects by retention interval. Memory. Memory by subjects. Memory by retention interval. Memory by subjects by retention interval. Done. 36, 37, 38, 39, 40, 41, blah, 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 59. Double check. Double check to get the right number of degrees free. But how do you know what to test with what? If you've done this thing in the order I just told you to do it, which is not my idea, it was an idea that Frank Yates had, one of the inventors of analysis of variance, called Yates order. You do it, you're going to test retention interval, mean square retention interval, you will divide by mean squared for subjects by retention interval. You just look at the one below it, the first one below it that has subjects in it. So it's like a mechanical thing. Memory, we're going to test that. The mean square for memory, you're going to divide that for mean squared by memory by subjects. Mean squared for memory by retention interval, the F test will be divided by mean squared for memory by subjects by retention interval. And you might be wondering, well, shouldn't the software know this? Yeah, it should. But a lot of times, especially because we have the shitty version of SPSS, you can't directly do this kind of analysis on the shitty version of SPSS. I could almost encourage you to steal the better version. I won't, because that will be wrong. But what I'm saying is, you could set this up in SPSS like it was a factorial design. It'll do all the analysis for you. Then it'll go, oh no error term. But it'll give you all the mean squares, and you can do the division yourself. So it's actually pretty easy. It's not the only reason I'm teaching this to you, but I'm saying that it makes doing an analysis like this possible with software that isn't really designed to do it. The other thing is, sometimes even when you do have software, let's say SAS, which I'd rather we had, but we don't. If you had SAS, or R, which is powerful as hell, and free, but it involves typing command lines in. It's not just clicking and pointing, so it scares people. You still have to, with those things, you actually have to specify error terms. They're much more advanced statistics packages, and they assume a level of knowledge on the user that's pretty high. So they figure, oh no, you specify the error term. Right? So you have to go through this. And finally, when you're setting up an experiment, when you do an analysis and it comes out and the degrees, you should be able to look at it and say, okay, what should the mean squares be? Like what mean square for what should I get? And secondly, what should the degrees of freedom be? Right? You should know that. And then when it comes out and the degrees of freedom are wrong or something, you should go, oh, that's a mistake. The first thing I do when I review an article for a journal is I draw the design out. And if they use analysis of variance, I go through this and do this myself and say, okay, let's just make sure they did the analysis right. Because you'd be surprised how many people just type things in their computers and trust the output. Lots of people. And I'm not saying I catch people all the time. And I catch, they're not trying to get anything over on me. They've made a mistake. So the analysis then is a lot easier. You can help people out when you're reviewing something, which is what you're supposed to be doing when you're the reviewer. So you're not supposed to be that dickhead reviewer, the person we all call reviewer 2. You didn't cite the paper I wrote in grade 4 on the U.S. Civil War. Why isn't that in there? I usually make little jokes. People always know it's me. I may be stupid, but I don't know what this thing means. I say things like that. Then everybody always knows it's me. You were reviewer 2, weren't you, Dave? Yeah. Well, I'm reviewer 1. Reviewer 2 is always the dick. So it's a running joke. It's an academic legend. Anyway, questions? Yeah, go ahead, Nick.
How many cups of coffee have you had today? Oh my god.
I used to drink lots of coffee, and I was way more animated than this. I used to be. You probably think that I'm pretty intense, right? This is the calm version of me. About 15 years ago, before I did, before the therapy, and I'm not kidding, I was a lot more intense than this. Okay, what's up?
Did we talk about unequal sample sizes in the last class?
No, not really. Maybe tangentially. And I probably said don't have them.
Oh.
Yeah. As a rule, it's better if you don't have unequal sample sizes. It makes your life easier on a lot of levels. There are ways to deal with it, but it's a pain. It's a pain. And generally, and the software will typically deal with it. Some software deals with it quite poorly, however. Other questions? All right. Thanks, guys.